Oh, to have lived in London. Should I translocate there? I'm not seriously thinking about moving to London, but rather sharing a mnemonic device for remembering the enzyme commission or EC numbers for the different classes of enzymes. And so that mnemonic stands for oxidoreductases, transferases, hydrolases, lyases, isomerases, ligases, and translocases. And I don't need you to worry about which number corresponds to what, but rather I want you to be able to classify enzymes based on the types of reactions that they catalyze, because that's basically how they're sorted in this EC number system. And we'll use a sort of rough sorting of them. We're going to see ligation carried out by ligases. We're joining things together. Hydrolysis, this is going to be carried out by hydrolases. We're breaking things with water. We have group transfer, which are going to be carried out by transferases. We're transferring groups, as it sounds like. Isomerization, so isomerases are kind of going to swap things around. Redox reaction are going to be carried out by our oxidoreductases. And elimination and our bond breaking in other ways are going to be carried out by our lyases. We'll talk about how these different enzymes do different things. So we'll talk about the different things they do, which is typically how we classify them, as well as then how they're actually doing it. So their catalytic strategies. I want you to be able to interpret the reaction mechanisms and identify the catalytic strategies that they're using. Don't worry, there's not that many strategies. There's a lot of the common tools that enzymes go back to over and over and over again. All enzymes are going to do what we call proximity catalysis or entropy reduction, where they bring things together in the ideal orientation to react. And then you have different types of catalytic strategies employed by different enzymes. Some of the common ones are going to be acid-base catalysis, where you're actually providing protons, and that's going to strengthen your electrophile and stabilize negative charge, or you're going to be taking protons, and that'll strengthen your nucleophile and stabilize positive charge. We'll talk about how there are a couple of different types. General acid base, which is what we're usually referring to, where an amino acid typically is going to be acting as an acid, and then it's going to be acting as a base, or it's going to be acting as a base, and then it's going to be acting as an acid. We also can have specific acid-base catalysis, where it's just the water ions in the water that were already present are acting as acids and bases without the involvement of an amino acid. Some enzymes, metalloenzymes, have metal cofactors, and those metal ions are going to help coordinate things, and metal ions are typically positively charged, so they're going to be able to stabilize some negative charge. Covalent catalysis, some enzymes are actually going to form a temporary covalent bond with the substrate. Most enzymes are just going to involve interactions with those intermolecular forces, and remember that they can form lots of different intermolecular forces with their substrate. And these are going to allow for lowering of the transition state as well as providing specificity. So we have a huge diversity of enzymes, and we can classify them in different ways. The enzymes are kind of going to mix and match these strategies, but all of them are going to be lowering the energy of the transition state. So remember that the transition state, when you have a transition state, that's when you have that really, really awkward state that the enzymes are going to make easier. In the transition state, remember, that is going to be where you have partial bonds forming and partial bonds breaking, and they're super fleeting, they're not isolatable, but we know that they have to exist. We know that Santa came because the presents are under the tree. We know that transition states have to exist because we can have intermediates on either side. And so the reaction intermediates are going to be the troughs so the low points in our reaction coordinate diagrams. And the peaks of reaction coordinate diagrams are transition states. And with the transition states, we're often going to show them with this double dagger symbol and put them in brackets. So let's review how we can look at reaction coordinate diagrams. So remember, on our x-axis, that's the reaction progress. On our y-axis, we have our free energy. And so if we want to look at changes in free energy, we want to look at the differences, so these deltas, between values on our y-axis. Remember the reaction progress, this is not like a set linear time scale, it's just the different steps in the enzymatic reaction. You'll see often a lot of curvy lines, and so the bottom's the troughs, the valleys, are going to be your reaction intermediates, and the high points are going to be your transition states, those really uncomfortable states. So you are going to be going from intermediate to transition state, and you might do this multiple times throughout the course of an enzymatic reaction. Each of those is going to be associated with a delta G double dagger, and the one with the biggest delta G double dagger is going to be the activation energy for that reaction. It's the slow step. It might not be the first one. It may be the first one. Enzymes are going to make it easier to get over that transition state. And they're going to be doing this by stabilizing the transition state. So the higher we are on our y-axis, the less stable we are. The lower we are on the y-axis, the more stable we are. And so we want to lower the energy of the transition state, making the difference in energy between the intermediate before it and that transition state smaller so that it's easier for the molecules to get to the transition state. Now, whether or not they stay on the other side, remember when they're at the top, they can go either way. They can go back to where they were before. So maybe they were going back to reactants, or they can go and they can make products. But then they can go back and forth. And because the enzyme lowered this barrier, that makes it easier in both directions. And if you were to let them go to equilibrium, well, then you have to look to the overall thermodynamic favorability, the difference in energy between your reactants and your products, this overall delta G, that the enzyme cannot change. The enzyme can only make it easier to reach the equilibrium, but it can't change the equilibrium that is reached. Okay, so now how are we going to actually lower the energy of that transition state? First is just that good old proximity catalysis. And so those IMFs, those good old IMFs, those are intermolecular forces. What those are going to do is they're going to help kind of prepay the entropic cost of bringing the molecules together. And then you're going to get the enthalpic gains from binding to the enzyme to help offset that cost. So remember that we can talk about enthalpy and entropy. And entropy, when we bring things together, that's kind of bad for our entropy because we're increasing the order instead of increasing the disorder. But when we increase the order, we might be freeing water molecules, so we might get some entropy gains there. And we're going to be making favorable bonds and interactions that are then going to contribute to our delta H. We're going to be getting a negative delta H, and all those bonds and interactions are going to help stabilize things. And remember, stabilizing things, we're going to be lowering the energy. And if we're lowering the energy of our activation energy, well, then we're going to be making it easier to get over it. We're also kind of increasing the local concentration, making it easier for things to find one another, and thus going to be accelerating the rate at which the reaction is occurring. So pretty much all enzymes are going to use entropy catalysis, and a lot of them are going to use acid-base catalysis, but not all of them. First off, let's clear up the terms general acid-base and specific acid-base. Typically, what we're talking about in enzymatic reactions is going to be general acid-base catalysis. This is where basically one of the amino acids typically is going to be acting as the general acid and base. Sometimes they're going to work through water, so they'll steal a proton or they'll give a proton to water in order to activate it. But the amino acid itself is going to be necessary to kind of kickstart the reaction. In the case of specific acid-base catalysis, that specifically uses water ions as the acid or base and relies only on the pH. So it doesn't need anything to activate the water. The reaction just relying on the natural concentration of those hydronium and hydroxide ions in the water that are present at a given pH. As I mentioned, we're typically dealing with general acid-base catalysis with enzymes, so let's dive in and talk about those. A confusing thing for many people is that any amino acid whose R group is protonatable, so it can give or take protons, must by definition be able to give and take protons, meaning that it can act as both a general acid and a general base. When we talk about a general acid or a general base, this is not referring to what we typically classify as the basic or the acidic amino acids. Yes, those ones can participate, and you can have the basic ones be acting as acids and the acidic ones be acting as bases. But when we call something basic or acidic in the context of classifying amino acids, we do that because we're referring to how they act in their neutral form. So in their neutral form, aspartic acid and glutamic acid, they act as acids. They give up a proton, they become negatively charged, so we often see them in their negatively charged states, in which case they would actually be able to act as a base. In the case of our basic amino acids, well, that would be histidine, lysine, and arginine. We call them bases because in their neutral form, they act as a base, take a proton, and become positively charged. In this positively charged state, well, this is their conjugate acid form, and therefore they'd be able to act as an acid. But they're not the only ones that can act as acids and bases. Instead, you can have any amino acid that can give or take protons. So we're talking not only about our acidic and basic amino acids, but also the ones with hydroxyl groups, the ones with thiol groups. So our cysteine, our serine, our tyrosine. All of these are going to be able to serve as general acids and general bases. Because remember that speeding up reactions over and over again without getting used up, well, that's the definition of what an enzyme does. In order to do that, it needs to be able to kind of reset. So if it gives a proton, it has to be able to take a proton in order to be able to give a proton again. In terms of our general bases, well, what's a base do? A base, in one definition, is something that steals a proton. And so by stealing a proton, the base is able to strengthen the nucleophile. Nucleophile is going to be stronger if it had concentrated negative charge. That's going to make the nucleophile like less happy and more tacky. Well, if we take a proton, we can then generate that concentrated negative charge, and this is going to then allow us to have a stronger nucleophile that can then go and attack our electrophile. So in this case, we see that histidine is deprotonating this water, which is then going on the attack. We call this a general base, not specific, because basically we need this amino acid here in order to activate the water, but it doesn't have to be a histidine. Any general base would work. Basically, we need something here that can take the proton from the water, but there's not enough ions in the water in order to do this reaction without help. Once you have this, you're stabilizing the positive charge that would be building up in the transition state, and this is going to lower the activation barrier. So with our general bases, this is what we're going to see is something like this. You can see that once an amino acid acts as a general base, well, now it's got a proton, it can act as a general acid. And in order to actually get reset, we need it to act as a general acid. We need to act as an acid, give up that proton, and become reset. So in a minute, we'll look at a ping pong mechanism that's commonly used. We see it a lot with histidines, where we can kind of go back and forth between the acid and the base form. But it's not just histidines that can do this, and the pKa is going to be totally skewed in the active site. So we can see things like an aspartate playing a similar role. So we'll discuss that more in a minute, but first let's return to the idea of our general acids. Our general acids, well, these are going to donate protons. We wouldn't want to donate a proton to our nucleophile, that would weaken it, but we do want to donate a proton to our electrophile, that can strengthen it. So even if we have a weaker nucleophile, something like water, if we've protonated the electrophile, basically what we're doing in this case, we're protonating this carbonyl group. This is going to make it so that the oxygen is going to be hogging even more electrons from this carbon, making this carbonyl carbon even more partly positive, which is going to make it more vulnerable to attack. And this is going to help catalyze the reaction. It can also help make for a better leaving group if you were to protonate what was be your leaving group, and it can stabilize the negative charge in the transition state, similarly to how we saw the general bases were stabilizing a positive charge. Both cases, you're lowering the activation barrier. Okay, so general acids and bases are awesome, and there's actually a lot of different amino acids that we can find them in. Let me show you a couple examples. RNase A is an RNase. It's an RNA endonuclease, and it's basically ubiquitous. It's everywhere. It's secreted by a bunch of different things in order to kind of protect from invading viruses, which are often RNA viruses, and so you don't want to have their RNA attack you, so you go on the attack first, and you chew up their RNA. In the case of RNase A, we kind of have a ping pong mechanism between two histidines. If we think back to histidine, this is one that we can kind of more easily see can go back and forth. It has a pKa around 6. The pKa refers to the pH at which half of something is protonated and half of it is deprotonated. If you go to a higher pH, there's fewer protons around, less than half of it is going to be protonated. And if you go to a lower pH, there's more protons around, more than half of it is going to be protonated. As we'll see in a minute, in the context of an active site, all bets are off with this pKa. But for now, let's just say, okay, yeah, we can see histidine can go back and forth, no problem. So let's see how it can do this in the context of an active site. Well, RNase A, its job is to cleave RNA. So it's going to break up this phosphodiester bond between these two RNA nucleotides. In order to do this, it's kind of going to activate the RNA to attack itself. Remember that RNA has that 2' OH, that OH that's missing, or dehydroxy in our DNA. And so by taking the proton from that, now you're able to make this a stronger nucleophile that can then attack the phosphorus, breaking this bond and leaving this cyclic product, which then it can break off. Note that because RNA has this 2' OH, it's vulnerable to this, but DNA doesn't have the OH here, it's not able to get activated in this way. When RNase A takes the proton, we activate this nucleophile. Now this can attack. In order to make this part a better leaving group on its own, well, now it's going to take a proton from this other side, from the histidine on this side. And so over here, what we have is this histidine is acting as a general base. It's taking a proton. And this histidine is acting as a general acid. It's donating a proton. And now we have the case where basically the situation is flipped. This histidine over here now has a proton and can thus only act as a general acid, not a general base. And this one doesn't have a proton, but it has a lone pair, so it can act as a general base, but not as a general acid. So what's going to happen now is the tables are going to turn, and this histidine is going to act as a general base, take a proton, and activate a water. The water is now going to be a strong nucleophile, which can then go attack this phosphate, and then this 2' OH can then go and it can take a proton back from this histidine that's acting as a general acid. Now we have the situation reset, and we can do this again and again and again and again. So again, we have this histidine acting as both a general acid and a general base, and we actually have two of them in the active site that are kind of swapping back and forth between their various roles. So as I mentioned, because histidine kind of has that neutral-ish pKa, it's easy for us to see that it can go back and forth. And in fact, in our bodies, we often see it, a lot of it in both of the forms, kind of just naturally based on the pH of the water. But it's not just enough to consider the pH of the water, we need to consider the pH of the active site. And this is a very important concept because, well, if we look at what we call the acidic or what we call the basic amino acids, we see that their pKa's, except for histidine, they're going to be wildly unphysiological. So aspartic acid and glutamic acid, they have these really low pKa's. That makes it so that typically the pH of our bodies are going to, or I hope the pH of our body is going to be way higher than that, and so they're going to be negatively charged. And in the case of lysine and arginine, they have such high pKa's that in our bodies, they're going to be typically positively charged. But that pKa is kind of just if it was a free-floating amino acid, and we don't have a free-floating amino acid in the context of an enzyme. We have these amino acids that are held in place in this active site that's kind of this protected location where there's a local context of the amino acids around it, as well as any substrates and things like this that are then going to alter the chemical properties of those amino acid side chains. So for example, let's take aspartate. If we look back at our chart, we see that aspartic acid has a pKa of around 3.7. So it would be very unlikely to be protonated on its own. But in the case of an aspartic protease, so a protease, here we're talking about cutting a peptide. So here we have an example of a peptide that we want to cut into. An aspartic protease is able to do this by using an aspartate as a general acid and general base. It actually has two aspartates in the active site, but unlike before where we're seeing a kind of ping pong mechanism, instead the one aspartate is going to be doing all the giving and taking, and the other aspartate is going to be altering the pKa of the first aspartate. What we need to do is basically we want to raise the pKa, we want to make it so that this is going to protonate. Having this aspartate nearby, well, now we have this negative charge. We have two negative charges next to each other. They would like repel each other, and this one would seek out more positivity. So it would actually be wanting to take a proton. It could take a proton from water, activating the water as a nucleophile that can go on the attack and attack this carbonyl carbon. So we have this aspartate that normally would not want to act as a base that is acting as a general base. It's taking a proton, activating the nucleophile, which can go on the attack. Once you have this, you kind of get this tetrahedral intermediate, and now our goal is to split that intermediate in two. We also have the aspartate that's now protonated, and so now it's in the protonated state. It can't act as a general base, but it can act as a general acid. So that's what it's going to do. It's going to donate a proton to this nitrogen. This is going to make it so that this can then leave, and we get this whole system reset. So in this case, we have this aspartate that's acting as a general base, and then it's acting as a general acid. Now it's reset so that it can act as a general base again. And the reason why it can do this is because it's next to this other aspartate. So remember that the pKa of the side chains, and well, anything, is going to be extremely context dependent. In these cases, we're just kind of giving and taking protons. And remember, we give and take a proton. We're not linking two molecules together. We're just adding or removing a proton. But sometimes we do see that enzymes will actually form covalent bonds, will actually link directly to the substrate, attach themselves to the substrate as an intermediate. And we call that covalent catalysis. Now let's look at an example of a protease where we actually do use covalent catalysis. So the same overall reaction is happening, but it's going a very different way. So let's look in a little more detail about our serine proteases. Basically, it has this cool catalytic triad. So triad, there's three catalytic residues. We've got a serine, a histidine, and an aspartate. And what's going to happen is we're going to get this oxygen to act as a nucleophile and attack the carbonyl carbon. But the serine, remember, isn't going to be a very good nucleophile as is. Because remember that the serine is not normally going to be deprotonated because it's got this high pKa of about 13. So we need to actually lower that pKa. So that would be the pKa in isolation, but in the context of the active site, we can actually lower this. And so how do we lower the pKa? Well, we lower the pKa by helping stabilize the negative charge, helping pull away the proton. These things would lower our pKa. And so we're going to find that we're going to have serine get its proton stolen by histidine, and histidine is going to make more basic, more wanting to take that proton by an aspartate being nearby. Basically, you have the pocket on the enzyme in the active site where there's like a substrate binding pot. Binding there is going to get that trio into position to get to work. So you wouldn't want things always to be activated, always on all the time. Instead, you only want to activate it when you have a substrate bind. So when the right substrate binds, it's going to fit nicely in the pocket of that enzyme. And the enzyme, remember, what's it going to stabilize? It wants to stabilize the transition state. We're going to have like that induced fit. The induced fit is going to help make it so that that trio is right in position to get to work. So the first things first, we got to pull off that proton from serine. And so how are we going to do this? We're going to do this using a histidine, but histidine, well, that's not a very good base, remember? And so how are we going to get histidine to be a good enough base to pull off a proton from something that's not a very good acid? This is where the aspartate comes in, because remember, aspartic acid is a great acid. It really wants to be in this conjugate base form. It really wants to be in this negative form. In this form, it can hydrogen bond with one of the amines in the histidine. By forming this hydrogen bond, what's going to happen is that when the histidine gets protonated, it's better able to stabilize that charge. So it has this kind of like negative charge that can help stabilize this protonated form. And so the histidine is then going to be able to take that proton. Once you've taken the proton, well, now you've got a strong nucleophile. That serine really doesn't want to be negative. So it's going to attack that carbonyl carbon. Now remember that the enzyme is helping everything be held in the right orientation to do this. It'll attack the carbonyl carbon. We get our tetrahedral intermediates. When we attack a carbonyl carbon, we get a tetrahedral intermediate. It is a real intermediate. It's not one of those transition states, but we did have a transition state in order to get here. So we had to form a bond to the carbon, and then we had to break this bond, this double bond, so to get to this tetrahedral intermediate. So in between those, we would have had a transition state where we would have those partial bond formations. Now what we have is basically we have this tetrahedral intermediate. Our substrate in this case is covalently attached to the enzyme because the serine is coming from the enzyme. This is our substrate, but we haven't broken our substrate yet. We've only broken one of those double bonds. And so now we need to break this off. And we want to make sure that we break it off the right way too. The enzyme is going to help in a couple different ways. Basically, there's this part on the enzyme, this called this like oxyanion hole. So oxyanion, because it has this negatively charged oxygen, and then amide nitrogens in the backbone of the peptide in this pocket are going to help stabilize this intermediate and kind of make sure that it's going to break the right way. So this intermediate is going to break down. What's going to happen is that the nitrogen in what was the peptide bond is going to steal a proton from that histidine. So this is going to be stealing this proton. This is going to break the first part off, but the N-terminal part is still stuck on the other part. So you still have part that's stuck to the enzyme, and then you have part that has been broken off. In order to use this enzyme again, we need to regenerate it. We need to basically kick off this other part so that we do things over again. What are we going to call this? This is going to be one of those general acid-base reactions. And in this case, we're going to be having a general base because this nitrogen is going to be stealing a proton, making this hydroxyl ion that can then go and attack the carbonyl carbon. You get the whole situation happening again, but this time, because you're doing it from water and not doing it from the amino acid, you're going to be breaking things off. And so you're releasing the rest of your product. And you can see that we have kind of like two transition states that are pretty similar because we have to do that reaction state twice. So what types of catalysis was that an example of? So that was an example of acid-base catalysis. That was an example of proximity catalysis or entropy reduction. Not a metal catalysis because we didn't have any metals involved, but it was a covalent catalysis because we were forming that covalent intermediate. So we saw that different enzymes could catalyze the same overall reaction in different ways. We could cut a peptide either with a serine protease, in which case we were using that covalent catalysis strategy. Similarly, we could use a cysteine protease, which basically does the same thing except with a cysteine instead of a serine. Or we could use an aspartic protease, which is actually going to use aspartates to make the water react. And there are even additional other types of proteases we could have, where we could have glutamic proteases, which are similar to aspartic proteases, but they use glutamate instead of aspartate. Metalloproteases that are going to use metal. All of these are just different ways in which we can cut a peptide using different enzymes. We can also have enzymes within the same specific types. So we can have serine proteases, and for example, that are going to catalyze different reactions. And when we talk about different reactions, all of them are overall proteolysis reactions, but they have different substrate specificities. Serine proteases get their specificity thanks to this thing called the specificity pocket that we had talked about, or the S1 pocket, that's kind of going to help orient things in place. So if we look at three examples of serine proteases, trypsin, chymotrypsin, and elastase. Trypsin cuts next to long basic residues, so lysine or arginine. Chymotrypsin, it cuts next to these bigger hydrophobic residues. And elastase, it cuts next to these small residues. If we go and look at the specificity pocket, which remember is where the substrate needs to bind in order to kind of get that catalytic trio into position to react, here we can see that these specificity pockets are actually going to be shaped to kind of recognize the things that we're going to cut next to. So in the case of trypsin, you can see this little kind of like red dot right here. This is going to be representing this kind of like acidic pocket. That is where the trypsin specificity pocket is. That's going to nicely complement this lysine or this arginine. So you have this kind of long, narrow pocket with a negative charge at the bottom that's going to be perfect for holding on to one of those lysines or arginines. In the case of a chymotrypsin, here we want something that's going to be neutral, but we also need it to be big. So here with chymotrypsin, you basically see this big broad channel that's going to be hydrophobic. And in the case of elastase, well, here we have this little channel and it's got these valines sticking out of it so that it can really only accept these really little things like a serine, an alanine, or a glycine. And in this way, well as with other reactions around here, we're able to kind of have specificity for a substrate and not be just cutting anything. And finally, we have metal catalysis. Metals are really awesome. They can do things like stabilize negative charge in that transition state, helping lower that activation barrier. We'll see that they can give and take electrons to help with redox catalysis. So we'll see this a lot when we go into metabolism. And we'll also see how they can kind of like form coordinate bonds. So basically, they form these dative coordinate bonds where a pair of electrons, such as on a nitrogen or on an oxygen, similarly to how we saw in our case of hemoglobin, they were basically forming coordinate bonds with the metal. And the metal has this big electron cloud, and this diffuse positive charge, it's able to form these coordinate bonds with a number of different atoms at once. And this is going to allow that metal to serve as a central coordinating hub. And it's also really great if you have a reaction that's going to use like ATP as a cofactor. ATP has that negative charge. The positive charge of your metal cation is going to help stabilize that and help make this reaction more favorable, and even do things like make the phosphorus in a phosphate group even more electrophilic by pulling the negative charge even further away. And often we're going to find multiple of these strategies at play within a single enzyme. So let's look at some examples of how enzymes mix and match these strategies in order to catalyze reactions. Here's one example, phosphorylation. Kinases are going to be the thing that's going to add a phosphate group. And they're typically going to add it to a serine, a threonine, or a tyrosine on the hydroxyl group. The phosphate group, or more technically the phosphoryl group, the oxygen is the one that comes from the protein. And then this phosphoryl group, these phosphorus and these three oxygens are going to be what's being transferred. And they're going to be transferred from ATP. This is going to leave us with ADP and a phosphorylated protein, or some kinases are going to phosphorylate small molecules. And we'll see this a lot when it comes to metabolic pathways, that phosphorylating those small molecules is a great way to do things like make good leaving groups. But for now, we're just going to look at this example where we're phosphorylating a protein. In this case, it's the protein itself that's actually going to have to act as a nucleophile and attack the ATP. The job of the enzyme is to make it easier for that protein, for that hydroxyl group on that serine or on that threonine or on that tyrosine to actually go and attack the ATP. What we're going to see is that in the active site of that enzyme, we're going to have a hydroxylate. We're going to have this negatively charged oxygen that's going to be able to act as a general base, abstract a proton from our serine or threonine or tyrosine, from our protein substrate, in order to make that a stronger nucleophile. And now the stronger nucleophile can go and attack that electrophilic phosphorus in our ATP. But in order to do this, well, we need a couple things. We need that ATP to be there, we need it to be in the right position, and we need that phosphorus to be particularly attacky. And so what we're going to do is we're going to use magnesium in order to help with this. Magnesium, remember, it's going to have this positive 2 charge. It's going to be able to bind to those ATPs and stabilize it. It's going to stabilize the transition state when we have this attack forming. It's going to stabilize the negative charges. It's going to pull electrons away from those phosphorus. So remember, the phosphorus is going to be electrophilic to begin with because the oxygens are pulling electrons away. And now we have the magnesium pulling electrons away from the oxygen, which were already pulling electrons away from the phosphorus. So now this phosphorus is going to be especially electrophilic and vulnerable for attack. We've used this general base to make a stronger nucleophile that then is going to be able to attack. When we have this attack happen, now what we're going to get is we're going to get the ADP pushed off. This is an SN2-like reaction, so it's going to happen in this concerted motion. We have the oxygen attack the phosphorus, and then we get the ADP kicked off. Before this ADP leaves, it can pick up a proton from that hydroxyl group that was serving as our general base in the beginning. So now remember, it has this proton, so it can't act as a general base again until it gives it back up, until it acts as a general acid. So it can donate that proton back to the ADP, make the ADP more stable as a leaving group by stabilizing the negative charge, and it can also then regenerate itself to do this reaction again, have the ability to act as a general base again. Speaking of that, what catalytic strategies are being used? So we just gave away the one that it's starting by acting as a general base. And then at the end, we saw it acted as a general acid. What else do we see go on in this reaction? We saw metal catalysis. We saw that magnesium sort of serving as that hub and stabilizing the negative charges, helping coordinate things. And we also saw proximity catalysis. We saw that the enzyme was helping hold things in the right orientation to react. So remember proximity catalysis, that's also known as entropy reduction. And we're basically going to see that with pretty much all the enzymes. One of the things we didn't see, though, one of the things that's less common is covalent catalysis, where we're actually forming a covalent intermediate in which the enzyme is attached to the substrate, or at least part of the substrate. So although there's a whole variety of different specific mechanisms, we can kind of break things up into a number of classic reaction types. And these are roughly classified by their enzyme commission numbers, or their EC numbers. Each of those numbers was telling us something about the enzyme. And the first number in that EC number is going to be the main class of those enzymes. And we have these 7 main classes, but for the purposes of this class and things, instead of actually focusing on the exact number of these different classes, but these are the basic types of reactions that we're going to see. So now let's look at a little more explicitly at these. So as I said, O2 have lived in London. And then they had this last class added these translocases. This is actually this really new class. There had been 6 classes traditionally, and then they're like, hey, there's actually a 7th class. And so now there's translocases, which are enzymes that move things like ions, often across a membrane. And we're not going to worry too much about the translocases, and you still won't see them referenced in many sources. But we will see these other types, and the reason why it can be helpful to know the numbers. And so I don't really care too much that you know, oh yeah, 4 is a lyase, except that when you go and you see an enzyme commission number, if you see a 4 and then you're like, oh, to have lived, and you're like, oh, lyase, then you can kind of tell what's going on. That being said, what I care most about is that you're able to go and recognize what's actually happening in these reactions and why we classify something as a lyase, or why we classify something as a hydrolase or a transferase. So let's go one through one in these different types of enzymes. In the case of an oxidoreductase, this is going to catalyze an oxidation or a reduction reaction. So remember our oil rig, oxidation is loss of electrons or electron density, and reduction is gain of electrons or electron density. Thankfully, with enzymes, the names often give away what those type of enzymes they are. And so we'll typically see words like oxidases, dehydrogenases, oxygenases, or peroxidases. You don't need to worry about how we kind of like differentiate between an oxidase and a dehydrogenase or anything like that at this point. This is just to point out some of the names that you'll see associated with the oxidoreductases. For now, what I care about is that you're able to recognize when oxidation and reduction are occurring. Next, we have our transferases, and what they're going to do is they're going to transfer functional groups. So one of the most common things we're going to see is our phosphate or a phosphoryl group. We'll also see things like a methyl group. We'll see things like amino groups. So all of these are going to be examples of a transferase, where we're transferring a group from one thing to another. So our good old kinase, that's going to be an example of a transferase. We have a group transfer reaction in which we're transferring that phosphoryl group. Next, we have a hydrolase. A hydrolase is going to break bonds using water. Break bonds using water. So it's going to catalyze a hydrolysis reaction. Some common examples of this are going to be our phosphatases, which are going to kind of undo the work of a kinase. We have phosphodiesterases, so this would be things like our endonucleases, our restriction enzymes. So an example would be our restriction enzymes. And we have our proteases that are going to cleave proteins. We have lyases. Basically, a lyase is going to make or break bonds without using water or without using redox. And so these are going to be a little harder to identify, but often what they're going to be doing is they're going to involve the formation and or the breaking of double bonds. And so we're going to see things like elimination reactions. So we'll point out some more examples of these, but know that this is kind of like one of the trickier things to actually recognize. An isomerase, this is one of the easiest ones to recognize. Here, we're basically just have to see where things are being swapped around in a molecule. When we talk about swapping it around, we're not changing the actual atomic composition. We're not changing the number of each atom, but we're just changing their arrangement. This could be just their arrangement in like 3D space, in which case we could have like stereoisomers that are kind of like our left and right hand. And that would be an example of a racemase that's actually doing that sort of conversion. One of the examples we've seen is going to be with the proline. Remember how proline could be that cis or trans conformation in its backbone? Well, this enzyme can actually go and convert between those two. Remember that when you have one of those configurational changes and not just a conformational change, you actually need to make and break bonds in order to do that. And so the enzymes can help with this. A mutase is actually going to shift groups around within a molecule and change what links where. And so we'll see some examples of both of these things at play. A ligase, here they're going to join two molecules together, typically with the use of ATP. Join two molecules together. Typically with the use of ATP. You might also see other NTPs, so you might see like GTP or something like this, and this would be an example of a ligase. So the ATP is often used to kind of like pay the cost of putting them together by reactivating things, making better leaving groups. But the ATP itself is not really being joined onto the molecule like we saw. It's not being the ATP that's being transferred in this step. It's actually going to be the molecules being joined together, but using the ATP as energy. And so we'll see some examples of this. And then finally, we have those translocases, which we're not really going to worry about too much in terms of their classifications. So now that we have a better idea about the basic catalytic strategies, so we've got our acid-base catalysis, we've got our entropy reduction or our proximity catalysis, which pretty much all enzymes use in order to kind of form bonds with the substrate, or more specifically with that transition state, that are going to lower that activation barrier, bring things in an orientation and place in order to react. Kind of offset the cost of the loss of entropy it takes to bring those things together. With some enzymes, we had our metal catalysis, where we had a metal ion that was actually helping like stabilize negative charges and kind of serving as that central coordinating hub, maybe making things more electrophilic. And then we had our covalent catalysis, where we saw that the enzymes could actually make a covalent intermediate linked onto the substrate or part of the substrate. We saw that enzymes could basically mix and match these strategies, but did so in order to carry out a sort of distinct set of different types of reactions. And we looked at how we can kind of classify enzymes based on their reaction type. In the coming weeks, we'll go into some more specific examples and see how enzymes are able to be so super duper awesome.